Okay. All right, so linearization. This is worksheet 14, 5.5. When you're asked to find linearization, again, it means find the equation of a tangent line. So remember, the equation of tangent line, or any line, really is just this. And remember, your slope is going to be dy over dx at x equals some number. In this case, x equals 2. So I got to find my derivative, right? Because that's the slope. It's a value of the derivative at a particular x value, right? So if I do my derivative, that's easy. That's 3x squared minus 2. Great. Let's add prime of 2. That's 3 times 2 squared minus 2, which is 10. So my equation of tangent is going to be y minus, and it equals 10 and then if you plug this in, eight minus 4 plus 3, you get 7. So that's part A. Part A is done right there. Now for part B, I'll change colors. What says use L of x. So really, if you think about it, you can actually rewrite this as y equals 10 x minus 2 plus 7, if you want to move the 7 over, and then you can replace the y with L of x. So that's what L of x just means, just so you know. It's just a function notation. It's nothing really crazy. You're fine with just writing the equation of tangent line. That's really what it is. But sure, let's write as L of x. Not a big deal. So you're asked to find f of 2.1 or use it to approximate f of 2.1. Well, then that's what I'm doing. Actually, I'm going to erase this because it's being a little distracting. So f of 2.1 is approximately going to equal so I plug in 2.1 into this right here. 10 times 2.1. So you plug in 2.1 for x into the tangent line equation, and you solve for y. That's really what you're doing. But since I isolated y already in green in the top left corner, so just plug 2.1 in for x and work it out. If you do, you get 10 times 0.1 plus 7, you get 7 points. If you get 8, actually. Is that 8? Yeah, you get 8. Now, let's use our calculator. Let's plug in 2.1. Minus 2 times 2.1 plus 3. It's 8.061, actually. So truly, it's 8.061. So clearly, our approximation is an underestimate. And that's what they're kind of asking us in part C, you know, whether it's greater or smaller. Obviously, we're smaller than the true value, but you can use concavity to help you determine that. Let me show you how you can do that for part C. But you can see that it's pretty close, right? And that's because there's something called local linearity. So if we go back to the notes again, there's something called local linearity or locally linear. When you take a graph and if you zoom in enough, the graph almost looks linear. Even though it might be really curvy or wavy, if you really kind of zoom in like crazy, and there's a little demonstration that I'd have students do. Obviously, we're not going to do it here in the interest of time. There's a little demonstration you can do in the calculator where, yeah, you can, actually, I think that's expression 2 right here. You graph absolute value of x and you graph this, but you graph this one, expression 1, x cubed minus 3x, which I know is wavy, but if you zoom in close enough, you will see that part of the graph kind of looks linear. But very important though, your function has to be differentiable though, at that value where you're trying to do a linear approximation. For absolute value where you have a sharp corner, you're gonna have a problem because you're not differentiable at sharp corners, so you can't use a linear approximation because you can't do the derivative of absolute value, right? At the vertex, it's not, you're not, the left and right hand derivatives are not going to equal each other, so you can't do that. It's not differentiable there. But coming back again to part C, so how can I use concavity to determine whether my estimate's greater or smaller than the true value? So we saw that our approximation was an underestimate because I computed what it was in part B, and then I actually plugged in 2.1 into this to see what happened also. But what you could do, you could use concavity also to help you. Let me show you how that works. So remember, f prime of x is 3x squared minus 2. F double prime of x is 6x. Great. Well, here's the thing. In this interval, f double prime is going to be positive. Okay, it's going to be positive. And what's happening here is that if you're concave up and you draw a tangent line, so you'd agree the green curve is all concave up, right? That's totally concave up. We would see that the tangent line is, of course, my approximation. The curve itself is the exact value. Of course, the approximation is less than the exact value. Just look at it, right? So when you're concave up, your linear approximation, or when you're using a tangent line to approximate the output for some input, and of course your input's very close to where the tangent line is located. Yeah, it's totally going to be an under approximation. Now, when you're concave down, on the flip side, that's a concave down function. Here's a tangent line, right? And we see that that's above this one, right? Yeah, that's totally above this. That's an over approximation. So when you're concave down for a certain interval, then we know that we're totally going to be under approximating. Sorry, our tangent line will over approximate the true value. So I know it sounds a little counterintuitive, but when you're concave up, again, the linear approximation is underestimate of the true value. When you're concave down, the linear approximation is an overestimate of the true value. And notice has all that stuff. So I think what would be good, if you guys may want to try number 2, perhaps, that might be a good problem. It's just very similar to what I did for number 1. If you have done number 2 already, then try number 3 or just ask me a question. But why don't you guys try right now? If anyone has any questions, feel free to fire away in the chat, and I'll totally handle that question for you. If any of you guys have done like this worksheet or even the textbook problems. The textbook problems, where did I put those actually? Post session, there we go. And you see like this, this kind of covers everything from 5.4, 5.5, and 5.6. You see there's a linear approximation for number 1. Number 2 is related rates. Number 3 is also, I think, related rates. And geez, I don't see anything on optimization though. That's weird. Interesting. Okay. Yeah, I'm surprised there's no optimization problems, but okay. Anyway, go and try number 2, and then we'll talk about it in just a second. I'm going to see if I can locate the answer key as well for that one. Actually, no, I don't think I have the answer key for that one. Come think of it, I don't think I do. Or maybe I do. Hold on. Yeah, I do. I do have the answer key here. So I'll show it to you guys in just a sec. So again, go and try number 2. Okay. The other guys are coming in in just a sec, so let me show you guys the answers for that one. So here it is. So if you haven't finished all the stuff for 5.4 or 5.6, definitely do that. Or if you haven't even started it, well, do it now. It's all the stuff's there in the folder. And of course, if you have to do some stuff for 5.5, do that as well. And yeah, you can see the answer for number 2 is right there. So you do a derivative of this, which is off to the right here. And then, of course, plug -4 to get the slope. So you have your linearization. So it's just equation of a tangent line. Plug in -3.9 into that, and that's the linear approximation. And then use concavity to see whether it's an under or overestimate. So you would have to then do the second derivative and see what's going on there. It is a little tricky to do because that is not a fun derivative to work out, but or second derivative to find. But what I really kind of care about is really more parts A and B. You could obviously use your calculator and kind of plug in a random value between -4 and -3.9 into the second derivative or the derivative of this. So you can punch this in and have the calculator do the derivative of this and plug in, like, say, -3.95 or something, and see if that's positive or negative. And that, or you could, of course, just plug in -3 into the actual function itself and see if our approximation is under or over approximation. So that's essentially 5.5 in a nutshell. Let me bring the other guys back in really fast, and we'll end our session. Let me close them. And let me